Hello my dear students, welcome to this session. Now last session we discussed case 2, right? I think you understood how we are writing the equations using normal traditional method as well as inspection method I have explained you, okay? So both the methods are important, I'm telling you. You must be good at writing the equations. You should not have a doubt, okay? So let's go with the case 3. Same network you note down, okay? I will tell you what are the changes that we need to make. Same network you note down, okay? Note down the same network. Case 3. Same network. But I'll tell you the reference node position at different place. Okay, please note down. Same network. Note down quickly. Case 3. Yes. Quickly note down the circuit. I think all of you noted down. Just let me take this off, okay? Okay. So write the equations now with reference node position at different place. Usually people select bottom node as a reference node. But let me select this particular node as a reference node. Let's see what will happen. This is V1, this is V2. Because sometimes when you change the reference node position, you will have a lot of advantage. You will have a lot of advantage if you change the reference node position. So for that reason, let us see first of all, if we choose a different node as a reference node, what will happen? Okay. Now, look at this. KCL at node 1. Tell me. V1 minus V2 minus E1 by R1. Yes or no? Okay, all of you understood this point? V1, but this is not 0 now. This is V2. V1 minus V2 minus E1 by R1. How it is? This point is operating at V1. This point is operating at what? V2 plus E1. What is the net potential difference? V1 minus of V2 plus E1. Nothing but V1 minus V2 minus E1 by R1. This is the leaving current. This is entering current minus I4. This is now leaving current V1 minus V2 minus E4 by R4. Once again, you can see this point is operating at what? Not E4. It is operating at V2 plus E4. With respect to reference node. Anything is with respect to reference node. Okay. Now another one here. V1 minus 0 minus E3 by R3. Or KCL at node 2. Assumption V1 greater than V2. Here V2 greater than V1. Yes or no? Now V2. What is the degree of it? 1, 2, 3, 4, 5. The 5 terms must come here. V2 minus V1 plus E1 by R1. Hope all of you understand. V2 minus V1 plus E1 by R1. Minus I4 or plus I4 because it is leaving current as far as node 2 is concerned. Plus I4. V2 minus V1 plus E4 by R4. Entering current as far as this node is concerned. V2 minus 0 minus E2 by R2. Or inspection. Understand all of you, okay? You tell me, what do you get here? Plus V1 of 1 by R1, yes or no? 1 by R1, 1 by R3, 1 by R4. Minus V2, common element between first and second node, and resistors and their reciprocals. R4, R1, their reciprocals. There are two paths which consist of resistive elements common to both first and second node. Therefore, 1 by R1 plus 1 by R4. You are supposed to take. Sometimes you may have more than one element common to both first node and second node. Is equal to, touching positive sign first, plus E1 by R1. Entering current this side negative, but that side plus I4. Touching positive sign first, plus E4 by R4. Touching positive sign first, plus E3 by R3. Now here, plus V2 of 1 by R1. I am looking at network, not looking at all this, right? 1 by R4. I can't get 1 by R3. This is nowhere related to V2. Yes or no? And this one I'm neglecting because this is in series with the current source. Next thing is what is left over here, R2. 1 by R2 is equal to, of course, here minus V1. What are the common elements? R1 as well as R4. I'm taking both of them, reciprocals. Now, V2. Here you are touching negative sign first. Minus E1 by R1. This is a leaving current as far as this node is concerned. Leaving usually plus this side, but that side it is minus. Minus I4. Now touching negative sign first. Minus E4 by R4. This is entering. Usually negative left side, but right side it is positive. Touching positive sign first. Plus E2 by R2. Second equation. You can directly construct the matrix form. Yes or no? Please note down quickly. I will write meanwhile matrix form and you please note down all these things quickly. The matrix form I am writing here. 1 by R1, 1 by R3, 1 by R4. 1 by here, 1 by R1, 1 by R4, 1 by R2, right? R3 is not related and R5 is neglected. Common elements, please. Here itself we can observe R1, R4, R1, R4, minus of 1 by R1, 1 by R4, minus of 1 by R1 plus 1 by R4. V1, V2 is equal to touching positive sign first plus E1 by R1 plus I4, that is entering current, outside always positive entering current, plus E4 by R4 plus E3 by R3. Okay. Now V2 like minus E1 by R1 minus I4. This is leaving current now as far as second node is concerned. Minus E4 by R4 plus I5 plus E2 by R2. That's it. Okay. It's very, very important case. Okay. Please quickly note down that matrix form also. Now let us compare the second case and third case. Let us compare the second case and third case. Okay. Note. Don't write anything, okay? I will give you some points. Okay, let us compare the second case and third case. How many nodes are there? 3 nodes are there. Don't write anything, I will give you time. Okay. Second case and third case, when you compare, in the second case, this node was taken as a reference node and you found V1, V2. Now I would like to find, taking this node as a reference node, what could be the values? Yes or no? Suppose after solving the equations, you got, let us say this is 10 volts and this is 3 volt. Now I want to find what is this V1 dash and V2 dash. Okay. If I select this node as a reference node, then what could be the node voltage here? Without solving the network again, taking this data into account, can you find V1 dash and V2 dash here? So networks are same. What is different here? Only the selection of reference node is different. The rest of the part is same. Okay. So therefore the networks are equivalent, no doubt in that. Both are equivalent. Yes or no? Then how do you find V1 dash and V2 dash? And what are their values? Okay. Look at this. What is the potential difference between these two? Branch voltage, 7 volts. Since the network is same, you must also get the branch voltage, how much here? Same 7 volts. Yes or no, all of you? Since it is 0, what must be the voltage here? 7 volts. Yes or no, all of you? So therefore you got V1 dash is equal to 7 volt. I repeat once again, although node voltages are different, but branch voltages remain same. Yes or no? Although node voltages are different, but branch voltages remain same. Therefore, you can see here, if this is the branch voltage is how much? 10 minus 3, 7. Then it must also be 7, but already it is 0. Therefore, it is 7 volt. What is the branch voltage here? 10. What must be the branch voltage? 10. But already how much it is? 7. What must be this voltage to get 10? Minus 3. 7 minus of minus 3. That is 10 volt. What is the branch voltage? 3. If it is minus 3, it is already 0. 0 minus of minus 3. Again you get 3 volts. You understand? This is one way of approach. The other way is that, now you tell me, if I want to get this case, what is the modification that I should make here? Okay, if I want to get the same case, because both are equivalent, right? To get this same case, what is the modification that we need to make in this particular case? Simply convert this into what? 0. That means you reduce this particular node voltage by 3. If one particular node voltage is reduced by 3, then every node voltage is reduced by the same value or not? There is a concept in the networks. If one particular node voltage is increased by certain amount of value, then every node voltage is increased by the same value. Decrease, then decrease by the same value. Therefore, here, if you reduce this voltage by 3, then you get 0. Then every node voltage is reduced by the same value. Therefore, this is equal to 10 minus 3. This is equal to already 0, right? 0 minus 3. Therefore, you got 7 volts here. You got minus 3 volts. You understand, all of you? Okay. That means, what do you understand from this? Do you have any change when you change the reference node position here? No. That means you can select any node as a reference node. That's why, please write on the point here. Okay. Any node can be selected as a reference node. Any node can be selected as a reference node. Any node can be selected as a reference node. Reference node. There is no full stop. There is no restriction. There is no restriction. Please note down this. Any node can be selected as a reference node. There is no restriction. Please note down this. Okay? Please note down this. Okay. Second point. Suppose you have reference node here with 0, this is 10 volt and this is 3 volt. If you select the reference node value as some 2 volt, then what will happen? It is also increased by 10 plus 2 as well as 3 plus 2. This is 5 volts, this is 12 volts. Yes or no, all of you? So reference node voltage need not be 0 because here you have 7 volts, here also you have 7 volts, here 10 volts, here also you have got 10 volts, 12 minus 2. Like that you are getting the branch voltage never change. Even if you choose the reference node voltage other than 0, okay, you will get the same branch voltage. Okay, that is why write down this point, second point. Reference node voltage need not be 0. It may be any other value. It may be any other value. Reference node voltage need not be 0. It may be any other value. But 0 is selected for convenience. But 0 is selected for convenience. Okay? This is very, very interesting points. Okay? 2 points are very, very important. Any node can be selected as a reference node. First point. Second point is what? The reference node voltage need not be 0. It may be any other value. But we generally select 0. That is for our convenience. Okay? Now, case 4. It's very, very important case in the entire. Okay? And most of the times in the exam, based on case 4 only, you are getting the questions in the exam. Okay? Please note down this, all of you. Please note down. I think all of you finished this, right? You finished this, right? Okay, then you please note down that. Okay. So for this problem, or for this network, how we obtain the equations, let us see. So listen to me carefully here. Now, how many nodes are there? 1, 2, 3. Say this is taken as 0. Then this is going to be V1. This is going to be V2. Let us see what will happen. What is the current flowing here? V1 minus E1 by R1. What is the current here? V1 minus 0 by R4. What is the current here? V1 minus V2 minus E3 by, see, there is no resistor. There is no resistor. Understand, all of you? When there is no resistor, how do you find the current? Yes or no, all of you? The current flowing here, if there is a resistor here, okay, R3, then what is the current actually here? You get V1 minus V2 minus V1 minus V2 minus E3 by R3. Slowly this R3 value is reduced to 0. Then what will happen? Then this entire value is approaching towards infinity. Yes or no, all of you? That means, is it really practically correct? When R3 is made 0, it looks like, from this expression it looks like infinite current. But do you really get infinite current in this path? When do you get infinite current in a path? Tell me. In a path, when do you get infinite current? Infinite current is possible in the given network only when KVL is violated. Yes or no? Infinite voltage is possible only when KCL is violated. But do you think that the KVL is violated in this network? Is it an invalid circuit? No, absolutely not. But this expression looks like a, wrong expression. You cannot prefer this, okay? If you connect an ammeter in series with this E3 on a breadboard in your laboratory, if you connect an ammeter here, definitely that current is going to be finite. That ammeter deflects to finite value, not to the infinite value. Therefore, there is a special procedure to apply node analysis for this kind of problems. Okay, look at this. The one approach, I'll tell you, that may not be recommended, but one approach I can tell you. Assume some current Ix. Okay, V1 minus E1 by R1, V1 by R4 plus Ix is equal to 0. That's it. Similarly, V2 by R5, V2 minus E2 by R2 minus Ix. Like that you can go. But what's happening here? What is happening? There are three variables. Understand? There are three variables. Now, unnecessarily you are introducing Ix here. Okay, therefore, what's happening here? Three equations are coming into picture. Let us not recommend this method. Okay, and we go for methods like super node analysis. Okay, method 1, I would prefer here. Method 1. Okay, what is it? Super node analysis. Okay, when do you apply super node analysis? What is the problem that you have encountered? First of all, tell me. There is an ideal voltage source which is connected between two principal nodes without any series resistor. That is the problem you have. That is why you are not able to apply, or that is why you are not able to find the current through that particular path using the Ohm's law. Okay, let us apply super node analysis. Super node analysis, in this step 1, let us take now. Please write down step 1, all of you. Write down step 1. Okay, write down, express node voltages in terms of voltage source value. Here, in this context is what actually here? E3 is the voltage, right? Okay. Now, can you tell me what is that expression you are going to get? V1 minus V2 is equal to E3. First equation. Step 2. Now suppress this particular voltage source. Suppress the voltage source, deactivating the voltage source. All are same statement. Suppress the voltage source is nothing but what? Replace by its internal resistance. What is the internal resistance? 0 ohm. 0 ohm refers to what? Short circuit. See, as soon as you replace it by the short circuit, that means its internal resistance, node 1, node 2 got merged and it is forming a common node. This common node is nothing but what? Super node. So therefore, it leads to the formation of what? Okay, which leads to the formation of supernode. Understand all of you? Okay. So what is a supernode again here? Let us define what is a supernode. It is the merge of. Please write down all these points. Suppress the voltage source which leads to the formation of supernode. Supernode definition. It is the merge of two principal nodes. Please do remember, two principal nodes. One principal and one reference. No, two principal nodes. Between which an ideal voltage source is connected. Please write down. Without any series resistor. Understand all of you? Okay. So this is a very important point to be noted. Okay. Now, if you replace this by short circuit, what is the circuit it looks like? This is short circuited, right? This is the super node. Okay. Now what we do is we get another equation, right? We need another equation. Already we got one equation, another equation. Now apply KCL at super node with previous branch currents. Hope you understand this. With previous branch currents. What was the branch current flowing here earlier? V1 by R4. Here V1 minus E1 by R1. Here V2 by R5. Here V2 minus E2 by R2. The same branch currents are flowing here. Yes or no? Same branch currents, same branch currents. Now apply KCL at this node. So what do you get here? Previous branch currents means here plus V1 minus E1 by R1 plus V1 by R4 plus V2 by R5 plus V2 minus E2 by R2 is equal to 0. This is the second equation. You understand, all of you? The previous branch currents we are maintaining here. Same V1 minus E1 by R1. Like that we are proceeding. Okay. So you got two equations and two unknowns. You can solve them. Yes or no? Okay. So please note down. I think all of you noted down up to this part. Only this equation and that network you must note down. What is the problem that you have encountered here? Why we have gone for super node analysis here? Tell me. Because there is an ideal voltage source. Don't forget that there is an ideal voltage source without any series resistor connected between two principal nodes. That is the problem actually you got. Understand? Now let's note down the same problem here with method 2. I'll put the title method 2 a little later after explaining that. Okay. Method 2. The same network I am taking once again. Okay, all of you write down, note down this network, draw this network. Okay, so what is the problem that you have encountered earlier? An ideal voltage source without any series resistor connected between two principal nodes. Yes or no? That's a major problem you have. Okay, but suppose if I choose this particular node as a reference node, out of these three nodes, if I choose this node as a reference node, just now, okay, we have discussed that any node can be chosen as a reference node. Yes or no? If I choose this one as a reference node, what is the voltage here? E3. E3 is a known value or unknown value? Known value. Every value is known here except node variables. Everything is known in the given network. So what is not known here? This one. I think one variable is enough. Yes or no, all of you? If I shift the reference node position from this to this, okay, I immediately come to know here what is value E3. Even if I select here also, I get minus E3. Yes or no? Okay, then I get another node here. I do not know the voltage. Now I can take V. Now how many variables are coming? Only one variable. See the beauty of this problem. When you have gone for this node as a reference node, super node was forming. Actually, there is no super node now. Yes or no? This is a principal node if you call it. In fact, it's not a principal node now because this is a value known. It's not a node variable. Yes or no? Now this is not connected between two principal nodes. Therefore, it is not forming a super node. Yes or no? How many variables you got? Only one variable. How many equations require? Only one equation. That equation you can write V minus E3. Remember, V minus E3 plus E1. Okay, I think all of you are good at writing the equations now. V minus E3 by R4 Now V minus 0 by R5. Now V plus E2 by R2. See this? Simple. Equation 1. One equation is enough to solve this network. Yes or no? Okay. But how many nodes are there? 3 nodes. How many equations require? Only one equation. Generally, when n number of nodes are there, n minus 1 equations required to solve this network. But this condition fails. What is the reason for that? There is an ideal voltage source. There is an ideal voltage source which doesn't have any series resistors. See, these are also ideal voltage source, no doubt. But this is having a resistor. This is also having a resistor. But this is an ideal voltage source which doesn't have any series resistor. In such cases, n number of nodes, n minus 1 equation, that condition fails. And who will decide the number of equations in such cases? If you take this one 0, you are getting 2 equations. If you take this one reference node, you are getting only 1 equation. That means who is deciding? The selection of reference node will decide the number of equations. That is why the selection of reference node is very, very critical and crucial. Okay. So I call this method as reference node shifting method. What is this? Reference node shifting method. Please put the title and write down here reference node shifting method. So what is actually reference node shifting method is saying here? According to this method, select, please write down, select any one of the terminals of an ideal voltage source. Which ideal voltage source? Which doesn't have a series resistor. An ideal voltage source which doesn't have any, which does not have any series resistor. As a reference node. Okay, as a reference node. According to this method, select any one of the terminals of an ideal voltage source which doesn't have a series resistor as a reference node. What is the advantage you get? If you take any one of these 2 terminals as a reference node, the other terminal voltage is immediately defined, and thereby the number of variables will be reduced and the number of equations will be reduced. Understand all of you? Okay. So please note down this completely. What is this method called? Reference node shifting method. Reference node shifting method is the best method to apply, okay, whenever you have ideal voltage sources. Okay, please note down this. Okay, so I think you have written this reference node shifting method. What is it saying? According to this method, select any one of the terminals of an ideal voltage source. Which ideal voltage source? Which doesn't have any series resistor. Okay, as a reference node. Understand? Okay. Now, put a note and write down. This is very, very important point. If the network contains n nodes, then the minimum number of equations required is n minus 1. Okay, is it clear? I think all of you know that very well. N number of nodes, n minus 1 equations. If the network contains n number of nodes, what is n actually here? N itself is the minimum number of nodes. Okay, if the network contains n number of nodes, the minimum number of equations required is also n minus 1, or is n minus 1. I'm sorry. If the network contains n number of nodes, then the minimum number of equations required is n minus 1. Okay, clear? Full stop. But this condition fails. When there are ideal voltage sources But this condition fails when there are ideal voltage sources without any series resistors. When there are ideal voltage sources without any series resistor. Clear? Tell me, who will decide now the number of equations in such cases? Selection of reference node. Yes or no? So full stop. Full stop and write. In such cases, the number of equations are decided by. In such cases, the number of equations are decided by. In such cases, the number of equations are decided by the selection of reference node. The selection of reference node. Understand? Okay. So look at this now. Justification once again. We have just now seen that, but still for this statement, I'm drawing the two figures and showing you clearly once again. So now you tell me the same network, if you take using supernode analysis, you are getting two equations. If you prefer reference node shifting method, you are getting one equation. Now, which method is advisable? Supernode is advantage or disadvantage in the competitive exams? Supernode should not be applied at all. Okay? So, this is E3, this is E2, E1, R1, R2, R4, R5. Okay? Same network I am drawing once again. Please draw it along with me, okay? Please draw it. Okay. So, if you select this node as a reference node, what's happening here? V1 and V2. What are the number of equations you are getting? If you select this node as a reference node, this is a known value, yes or no? Then this is an unknown value. What is the number of equations? Okay. Then from this you understand minimum number of equations is what? 1. Now in the exam, he will ask you the questions like, given the network, okay, what is the minimum number of equations, he will ask. How do you answer that? Minimum number of equations required. Sometimes he will mention using mesh analysis, what is the minimum number of equations? Using node analysis, what is the minimum number of equations? Or else he never mentions anything about the methods. It is of your headache to apply the methods, but tell me what is the minimum number of equations required. In such cases, you are supposed to answer. First, you find minimum number of equations using mesh analysis. Again, find minimum number of equations using node analysis. Then minimum of these two is going to be your answer. Understand? Okay. This is how you need to answer. Okay. So I think please note down quickly. I'll give you some examples. Okay. Meanwhile, I just note down here examples. Minimum number of equations required to analyze this network. Okay, I think you finished that part, all of you. Now look at this. What are the minimum number of equations required? Note down this quickly. Using mesh analysis, how many equations? 3 loops minus 2 current sources. 3 minus 2, 1 equation. Using node analysis, how many equations? This is 1, 2, 3 nodes. 3 minus 1. Reference node is there, right? Okay, 3 minus 1, 2 equations. So minimum number of equations required is 1, and you are able to achieve that through mesh analysis. For this particular problem, which method is the best method? If I ask you, what do you tell? Okay, don't tell your personal interest whether it is a mesh or node. You may be having your own interest. That is a different story. But the answer to the question which is the best method is always with respect to, okay, minimum number of equations. Whichever the method is giving me the minimum number of equations, that is the best method. You understand? Okay. So this is how you can answer it. Second question. Suppose if I make changes. Okay. Now what do you get? This problem will give you mesh analysis. How many equations? Mesh analysis 1, 2, 3, 3 minus, oh, this is the current source. Okay. 3 minus 2, 1 equation. Node analysis. You must remember when you apply node analysis, okay, you must immediately look at the network and see that whether there are any voltage sources without series resistor. Yes, there is a voltage source without any series resistor. That is an advantage for you. If you select this node as a reference node, then this is a known value. Yes or no? If this is 10 volts, this is 10 volts. Now how many nodes? 3. Out of 3, then 2 node voltages are, one is 0, the other is 10. This is the only variable which you do not know. Therefore, node analysis will give you only one equation. Mesh analysis is giving one equation. Node analysis is giving one equation. Therefore, which is the best method? Both are the best methods. Please note down. Please note down. Okay, if I give third case, please note down this quickly. Suppose if I give voltage source here, what will happen? 1, 2, 3. Mesh analysis will give me 3 minus only one current source, 2 equations. Node analysis will give me here, look at this, 1, 2, 3, but there is an ideal voltage source without any series resistor. If I take this is 0, this value is known. If this is 10 volts, this is also 10 volts. I do not know here. So one variable is enough. That's it. Now which is the best method here? Node analysis is the best method. So when a network is given, you cannot conclude just like that, without seeing the network, which is the best method. You tell me, you have to answer that, which is the best method means you give me the network, then I will tell you which is the best method. Understand all of you? Okay? So this is how you need to understand, and next session we will see the problems. So I'm going to stop here.